Exponential functions are functions that change at a constant percentage rate. They involve an initial value and a percentage rate of change. This makes exponential functions similar but yet different from linear functions. Like linear functions, they do have the initial value, but unlike linear functions, the rate of change is not constant. It's actually a percentage change. And so in some cases, as time goes on, the rate would actually increase if we were thinking of slope, and in some cases decrease if we're thinking of slope. But we'll actually have a constant percentage rate of change. Examples of real-world situations that lend themselves to exponential functions are compound interest, some population growth or decay, and radioactive decay. Let's take a look at an example, and we're going to take a look at growth as a constant percent rate of change as we look at a bank account. So let's suppose we have $1,000 and we're investing it in a bank account at 3% per year. We are not going to take any money out of the account, and we're not going to add any additional money other than the interest that gets accrued. What I would like to do is determine how much money is in the account after T years if the interest is compounded one time per year. In other words, if I add all of the 3% interest on once every year. So at time 0, when we first start this, we'll have $1,000. At the end of 1 year, we're still going to have that 1,000 because, again, we didn't take anything out and we haven't put anything in. But we're now going to add on the interest. And to compute how much interest we add on, we take 0.03 and multiply it by the 1,000. Now, instead of actually getting the number, I'm just going to simplify this a bit. And I'm going to notice that 1,000 plus 1,000 multiplied by 0.03 would allow me to factor out that common 1,000. And if I do that, that leaves me with 1,000 multiplied by 1.03. Again, I'm not going to multiply this out. I want to notice a pattern that's going to come about, that's going to give rise to the formula that we plan to use. So at the end of year 2, we would have the year 1 money, which was the 1,000 multiplied by 1.03, and now we need to add on new interest. So that would be the previous years, the 1,000 times 1.03, multiplied by 0.03. Again, I'm going to factor out what's common, and what I notice what's common this time is the 1,000, but also 1.03. And when I take those out, what I'm actually going to be left with is another 1.03. So I end up with 1,000 multiplied by 1.03 squared. By now, you're probably starting to notice the pattern. If, in fact, we did it one more time and we went to t equals 3, we would do the same process. Take year 2's money, add to it the interest on year 2, which we get by computing 0.03 times the year 2 account money, and doing a little bit of factoring and simplifying, and we would end up with 1,000 multiplied by 1.03 to the third. If we were to do t equals 4, you would probably imagine we'd have 1,000 multiplied by 1.03 to the fourth, and so on. So in general, if we were at year n, we would end up having 1,000 multiplied by 1.03 raised to the n. So now if we take a look at this formula, what we might notice is that we start with the 1,000, that's the initial amount of money that we had, and then we have the 1.03, which every time that we did this really came out of taking a 1 and adding 0.03, the interest rate, and then raised to the number of years that we were taking a look at. This is exactly what the formula indicates to us that we're going to use, the function we're going to use. So by definition, an exponential function q equals f at t has the formula f at t equals a times b to the t, or we could rewrite it as a times the quantity b to the t, with b greater than 0. So b will always be a positive number, so where we put the t or how we put the t isn't going to be critical to us. And in our formula, a is going to be the initial value. Yes, it will be the y-intercept as we're looking at things of this form. So the value at t equals 0. And b is going to be what we call the growth factor. If b ends up being greater than 1, as it was in this case, the function models growth, and if b is between 0 and 1, the function models decay. So that's going to be our setup, and our b will not equal 1. We will not have an exponential function if b is 1. So if b is greater than 1, we have growth. If it's between 0 and 1, it's going to model decay.